Today's lab is about the unconsolidated undrained test performed on saturated clay. We're going to use a triaxial cell like this. You can see there's a loading rod at the top passing through a sealed bearing in the top of the cell. And underneath that load rod is bearing on a top cap. And our specimen size is quite small. It's about a 1.4 inch diameter specimen. Top cap here and a bottom cap. If we wanted to use the same cell later for a consolidated test, we have access through these ports to the drainage lines, either at the top, at the bottom, and to fill the chamber with water, but we're not going to do that today. First though, we need to trim the specimen to be the size of this wooden dummy sample. So we'll get started with the trimming process. First, we're going to run an unconfined test just so you'll be able to see the sample better. So we're not going to have a chamber at all, but if we did want to have a confining pressure, we could put the chamber on when we're done and run the test with a pressurized chamber with confining stress all around it. We're going to be testing soil from the undisturbed samples that we took in the field. And this is the same sample that we ran the lab vein test on earlier. So notice how we ran it off in one corner. So we're going to have room, if we divide this into quadrants, to have 3 separate triaxial samples of this diameter without being too close to the edge and without being too close to each other. So we need to extrude a slice of soil that's a little taller than this so that we can trim it down to the proper geometry. We need spacers the right height here so that our sample doesn't push too far out. A little crack there. Okay. Soil is a little cracked here. That's all right. Take our wire saw. Cut this straight across the top. Glass plate ready. Just gonna slide this off to the side, keep it in compression. I'm squeezing with my hands. I'm not gonna fail it just with my hands. It's a big sample. And we're ready to work on this quadrant. We're going to use the same wire saw now to quarter the sample, and we'll try to avoid area here where there's a little bit of a crack as well. We want to go straight down, slicing a little bit as we go. Want to avoid the tendency that pretty much everybody has of pulling a saw toward them as they go down. Try to consciously go straight down. And then don't pull the saw back out again, but pivot from the bottom. I'm squeezing from the bottom. Separate the 2 halves. Make some space, then take the saw out and make the other cut. And we have our quartered sample. You can slide in a little spacer here to grab this. Separate these 2 quarters. Separate these 2 quarters. Of course, in the center of this quadrant, there's a cylindrical failed material. So this is a good sample to use for Atterberg limits that represents the soil in this sort of range of depths. And that's depths from which you're going to have some triaxial data for UU and CU, as well as the vein shear test. So it's good information to have the Atterbergs from there. So now we're about ready to trim the specimen down. We can slide this material back and bring forward this trimmer, which was made to trim only this size specimen. So it has protective posts or columns here. So when I go to use a wire saw or the blade that we're going to use later, as long as I keep the saw on the outside of those posts, I can't get too close to the center of rotation here. I can't accidentally make my specimen too small. So there's actually two distinct sides to this trimmer. The back side here says finish on it, which means I'm going to start on the start side. And those walls are a little bit further away, so that gives me a little extra room to kind of see what's in there in the specimen before I commit to a final position. So I'm going to lock this up in place, reach through, grab the specimen, set it on the post. The bottom cap of this trimmer is actually bigger than the sample bottom is going to be, the diameter. So you don't have to worry about covering the bottom cap of the trimmer entirely. It's the top cap here that's similar. So we want to make sure we're in a good position. Again, not too close to where the tube wall was, not too close to those cuts. I'm going to push this down firmly but gently and lock that in place. Anytime we want to turn the specimen, we're going to turn it from the bottom, and the top is just going to go along for the ride. If we turn it at the top, we might do a little torsion test and find the silt seams that are in there or something like that. Don't want to do that. So we're going to start on the coarse side, or the larger size diameter, with the wire saw. We have a water content can here. We've already got a tear mask for that. So again, I'm going to trim away just the outermost material, and I'm not even going to use that for the water content. That's plenty right there. So I'll go and get a water content of this and then finish the trimming by knocking off all the corners, turning it very slightly each time until we can't really remove any more material from this coarse side. So I've finished using the wire saw on the coarse side of the trimmer. If I turn the trimmer that way, what you'll see is some of the soil actually won't even come off. It kind of sticks to the sample because of the high plasticity. But I've got a nice cylindrical sample, and this is the time to look and see if you maybe have a band of organics or something like that. You probably see it. But now we're going to turn the device around, and instead of using the wire saw, we're going to switch over to using the trimmer, the steel trimmer. So this is basically just a bar of stainless steel with a highly sharpened edge. And when you're using this tool, you want to be very careful that you don't let the whole flat back of the blade stick up against the soil at all. So it's really important to keep an angle away from the guides up here. And then we're just going to slide this down from left to right, slicing off the soil as we go. This is the finished side of the trimmer, so we're basically looking to get a nice cylindrical sample surface out of this trimming. If I make large turns here, I'm going to end up creating more vertical corners. I'll have to go around again. That's what I'm doing this time. The other option is to turn it very slightly each time, and then you only have to go around once to get a cylinder. I'm not sawing back and forth, right? I'm just going in one direction. In this case, left to right. I'm keeping that positive angle. That's really important. You pull a big chunk of bay mud right out of the side of the specimen if the stainless steel surface on the back of the blade grabs onto the soil. Very sticky. So I'm almost around the first time. And as I mentioned, because I'm turning this pretty quickly, I'll go around once more just to knock off the remaining corners that I'm leaving. Not really a cylinder quite yet, so turn off the video while I do that. Save you a little time. So I finished using the blade on the finished side of the trimming jig here, and so it's time to take the specimen out and prepare it for the chamber. The way we're going to do that is to loosen this clamp at the top first, and then the most delicate part maybe is now where I need to separate that top cap from the sample. I want to keep the soil in compression, so I'm going to gently squeeze a little bit just at the very top underneath the cap. Wiggle that cap a little bit, make sure that it doesn't get stuck there. That was an easy one. No damage. Then I can take the whole pedestal out. We can see what we have here. You can see there's some voids, some imperfections. Natural soil sample may have that. In general, I would suggest not filling those in with soil unless you're really interested in what the soil density is. We could remold a little bit of the cuttings and put it into the voids if that was crucial to us, but this is, you know, the way the soil is in the field, so that's what we're trying to figure out and measure properties for. So I'm going to now take the sample off the base by twisting a little bit. I'm holding the bottom. All the weight of the soil above that's keeping it in compression. You can see there's some little pins that help hold the soil on the base of the trimmer there. And then we're going to use this split mold that's set to be the right size. So you see our sample's taller than it needs to be, but it's been trimmed to the right diameter. So this split mold is set up to be that same size. I can take it apart. I want to support the soil in the mold before I lay it down. And I can slide it along a little bit. I want to make sure the letters on the mold line up. A and A, that's good. And there we go. So this is mostly to support the sample while I trim the ends off to length. I want to rotate the mold so that the split is vertical, so that when I cut the end off, the wire saw can't slide right into the soil. I'm just going to cleanly slice that off. Little disc. And another little disc. This end. Pull it back up again. It's actually upside down from the way I started. Again, a little void there, that's okay, that's what's in the soil. So now this is my finished soil specimen. So this is what I want the mass of. And so what I did is I went ahead and weighed the bottom half of the mold, sort of like a tare weight for a water content can. So I know the mass of that. Now I can go weigh both of them together, and I can know what my moist soil weight is without handling the soil too much or having it stick to the scale. It's time to set up the chamber to accommodate it. And for a UU test, it's not too crucial about the seals, but we'll go through that anyway. I'm going to need that for the CU testing later as well. So we're going to put a membrane over the soil, and for the UU test, the main function of that is to keep the specimen from drying out. It's only been a couple of minutes, but when it's your first time doing one of these tests, it might be a little longer, so we want to get a membrane on there. We're going to use old traditional, high quality, low leakage, very thin membranes that don't carry a lot of load. But of course we got to cut the end off first. So want to be really careful when you're putting these membranes on, that you're putting it on in such a way that it will be easy to unroll over the specimen. And I'm going to roll it up over the cap first, make sure there aren't wrinkles there, not a lot of extra membrane. And we're going to put an O-ring on. These are Bunan rubber O-rings that are going to seal the membrane onto the cap. So their relaxed diameter is smaller than the cap, so I have to stretch them over the cap to get it on there. And I'm going to roll it down for now. I'm going to roll this down for now. Put a porous stone in place. There's a lip on the bottom cap, so the stone fits there nicely and doesn't slide around. So now we're ready to put the sample in. Again, always keeping the soil in compression. I'm going to support it at one end, stand it up, and then push to sort of slide the sample out of the mold. Hold it from the bottom, not the top. Get it into place. Okay. Then we're going to have a similar system at the top with another porous stone and another lucite cap. So we can place those. But the actual placement of the membrane, the unrolling of the membrane, can be pretty disturbing to the soil. So we want to help ourselves out by having some support. We're actually going to put the top of the cell on the bottom temporarily. Make sure it's in well. And we're going to tighten up this lock. This is a clamp on the top of the cell that prevents the load rod from moving relative to the cap or the cell. So now the whole mass of the top of the triaxial cell is resisting upward movement, right? And so I'm going to unroll the membrane up all the way up over the soil and onto the top cap without stopping. It doesn't have to be really fast, but it has to be continuous so we don't give the membrane time to kind of squeeze in on the soft soil. So here we go. Rolling it up onto the cap. No problem. Okay, I'm going to undo a couple of steps there then so we can see what's going on. Take the rod out. Okay, and you can see the membrane now is wrapped all the way up over the top of the top cap. I can hold my hand around the cap there. We can put this second O-ring seal on. And we're pretty much ready to go. One thing I didn't mention, but is important to note, we want to know the density of the sample, and we have the mass. In order to get the volume, we're going to just measure the volume of this cylinder in the mold to which we trimmed it, right? We trimmed it to be exactly that tall, and it fits into this diameter based on this trimmer. So we actually get as good or better an answer that way than we would trying to delicately measure diameters around this soft clay sample. So now we're ready to reassemble the cell and run the test. So again, if it was a confined test, it could be unconsolidated and undrained, but still have confinement. We're going to run an unconfined test, which means we don't even have any lateral pressure around the outside. So we don't really need the chamber at all. So we're going to leave that off. Going to put the top back on. We have some wing nuts. We want to be able to measure the change in height of the system while we're actually running the test. And so we're going to actually instead of putting a wing nut on the back, we're going to put this post, which is threaded. So it's going to still act to hold the top on, but it will also serve as a reaction post for mounting the LVDT we're going to use to run the test. So we'll set it up on the frame over there. Just going to put it on for now so I carry it over there. But we run these UU tests in the most primitive way using increments of mass and dial gauges and manual readings, just to kind of go back to the origins of the testing, right? Make sure you really realize how weak this stuff is by how little weight goes on. We're going to take it over to the testing frame and run the unconsolidated undrained triaxial test. So we have our UU triaxial sample set up here in its chamber without the cell itself, because we're not going to pressurize the soil. It's going to be unconfined. I've got the load rod underneath this crossbar, this hanging frame, and the dial gauge that we're going to use to measure height is resting on top of that crossbar. And the bottom of this frame goes through the table, and it has a hanger underneath the bottom, so we can apply dead weights to the hanger, and that load will be transferred directly to the soil through the system. And in the back, this green cylinder is a counterweight, which has been balanced so that the loading frame itself, which runs through a pulley up here at the top, is neutrally buoyant. So the frame itself doesn't exert weight on the soil. What I have done is I've added a small seating load. In this case, it's 200 grams. And that's to make sure that all the elements of the system are in good contact. And by definition, a seating load means that we haven't experienced any strain yet. So this initial dial reading, which I'm going to call 6.81 millimeters, is the reading for zero strain. Now, as the test goes on, the soil's going to get shorter, the frame's going to come down, this reading's going to get smaller, so we're going to take readings that are less than that initial reading of 6.81. But just like with an LVDT, with a dial gauge, I'm only interested in changes in those values, right? Importantly, though, the load does count as a load. So I have those 200 grams on there. That's 0.2 kilograms, right? That does count as load toward the cumulative stress that we're going to see as we run the test. So the way this is going to work, we're going to run sort of step loading. So every minute, I'm going to add another 1/4 kilogram load to the bottom. And right before I put on the next load, so at the end of the minute, I'm going to take a reading of the height that corresponds to the existing load. And then right after that, I put on the next weight, I wait another 55 seconds, and I take the reading for that load. And we do that until we get failure. I have almost 5 kilograms worth of weights here. That should be plenty for a bay mud sample from this depth. I'll just do the first few increments with you, and then we'll pause for a bit and pick it up later in the test. Skip the boring part. Put the first load on. We're still at our initial LVDT reading, and then I'll immediately start the clock, and off we go. Start. So we can see a deformation already, a little bit. These are hundredths of a millimeter. One full revolution of this dial gauge is, of the big hand, as it were, is a millimeter. So the little gauge on the inside is keeping track of the millimeters themselves. And in the early increments, what we see is we see some deformation initially when we put the load on, and then things pretty much stabilize. But we want to be consistent and always take that deformation reading about 5 seconds before the next load. So this deformation reading is going to be 6.77. 5 seconds. Here we go. We've got another 4 or 5/100ths displacement. I put on the 7th weight, and we've gotten about 0.4 millimeters total of displacement, so it's pretty stiff initially, as we might expect. Typically, we like to have the test last between 12 and 15 minutes, so we get enough data points to actually be a significant stress strain curve. So this is coming up on increment 8, and it's still looking pretty stiff, so I think we're in pretty good shape that way. So the reading now is going to be 6.3. You can see it's actually drifting now slowly between the readings, so 6.33. That's that creep we've talked about with bay mud. We don't want to wait indefinitely before the next increment because it'll keep creeping. Okay, and that is load number 9 actually on there. So the 12th weight is on there, and it's a little hard to know when these things are going to go, so I'm just going to leave the video on. We're putting load 14 on right now. 7.2. Each increment is deforming 3 or 4 times as much as it was for the first few increments. That was load 14 on there. So that's about 3.5 kilograms. Not that much, right? But it's a relatively small specimen. But visually, we can't really see much of anything, right? 1 millimeter, maybe 1.5 millimeters of displacement. Hard to see anything going on in the soil. The displacements tell us otherwise, though. Displacement is accelerating. Fortunately, I have a lot more of these weights in case we need them. That was load 15. You can see the dial gauge moving now consistently. We're about halfway through our minute. So we need to wait to the 55-second point. About 1/4 millimeter in this increment. 5.27. Always write it down after I put the load on. The displacement's already up there. It's moving a little bit in kind of periodically. That's because there's a very slight oscillation in the hanger. Hard to avoid that, but reading is now 5.00 and going kind of fast. So we're approaching 2 millimeters of displacement. That's maybe less than 3% strain. .88, and time to put the load on. This might have been the last one. That was load number 17. And it's not even oscillating now, it's just continuing to sweep out deformations here. But if we get to 55 seconds, I need to take a reading, because that's the plan. So it's now 4.3, 4.25, 4.18, and I need to put on the next load, 4.18. Okay, there go the displacements. That's got to be the last one, because now our strains are going up very quickly, and it's stress controlled. So we get a dramatic failure at the end of the test. And importantly, almost always when you run this test, because of the way we ran it, the last reading that I have for displacement is for the previous load increment, when I took it at 55 seconds. Then I put another load on. I can't read the dial gauge now, right? But that last load is the load at which failure happens. So you want to be very careful when you reduce the data to note that the failure load is the one for which you didn't get a displacement reading. So, unlike usually here, the sample actually sort of cooperated. You can see really sharp failure surface. So it localized, sort of like the dense plane strain sand sample would do. But this is, of course, very different. This is a very low density, saturated, undrained test. So we can talk about why that is, but this is the sort of thing you should expect. So we had 18 increments of 1/4 kilogram each plus our seeding load at failure. From here we would just take it apart. Often in lab we run 2 of these tests in one lab session. We run the unconfined test, and then while this is going on, someone in the lab group can be trimming a second specimen from the same depth, another 1/4 of that slice, and we would run a confined test with the chamber in place and applying some air pressure inside to simulate the in situ stress, and repeat the test to compare the strengths.